What we're going to look at today in this lesson is the difference quotient. And we've got it written right here. It's f of x plus h minus f of x, all divided by h. And provided that h is not 0, we always know that we can't divide by 0. And so this is what we call the difference quotient. Now, let's look at it in just a little different form. If we look at this as a graph, and we call this value right here our x, and then the distance from x to this value, let's call h. So this point right here then is actually x plus h. Now those are our x values. Okay, our y values, remember, is the same as our f of x. So our y value at this point is f of x. Our y value at this point is f of x plus h. Now, when you go back and look at our difference quotient, we're saying it's f of x plus h minus f of x. Well, that's this y value minus this y value, divided by h. Well, h is the difference between this x value and this x value. So this is very similar then to what we've dealt with before, that we have y sub 1 minus y sub 2 divided by x sub 1 minus x sub 2. And that's what we call our slope. So the difference quotient is just another way that we have of finding the slope. It's the change in the y's over the change in the x's, how much the x's changed. You might say, well, I already know how to find slope, so why do I need another formula to be able to find slope? Well, we know how to find slope for a line, for a linear function. As you move on into your math, and especially if you move on into calculus, then you're going to be wanting to find slopes of other equations. And those other equations aren't going to be lines. So here we have a parabola, and we may be able to talk about the slope at a point that's tangent, or the slope of a line that's tangent to a point on the graph, but that's going to change as you move around. It's not always going to be that same slope. If we found the slope at the point that was tangent let's talk about the point that's tangent at that point of the graph. Well, it would be different. You can tell that it's not nearly as steep as this point. Or what about the slope of a line that's tangent to a point of the graph over here? Well, you would have a negative slope instead of a positive slope. And your slope is going to be changing as you go around. So when you get into calculus, one of your fundamental parts of calculus is a derivative. And what the derivative actually does is it helps you find the slope of your equation at any given point on that equation. And the derivative is based upon the difference quotient. So in this lesson, we're going to be looking at some things that you will see again as you move on into calculus, and it will help you, but it's just based upon a function and our function notation. So let's take one that we're going to actually know the answer for before we ever start, but we're going to use it to help us learn this so that we can then use it on equations that we wouldn't know the slope as we started. So let's start with our equation f of x is equal to x plus 3. Now we know from algebra that the slope of this line is 1. We already know that. So we know what our answer is going to be. It's going to be 1. But let's use our difference quotient to see how we would get that. Now we're going to talk about f of x plus h. So what that means is we're going to take our function f. Wherever there's an x, we're going to substitute in x plus h. And we won't always write it out separately, but I want to this first few times. So that means we take our function named f of x. Wherever there's an x, we put in x plus h. Then plus 3. So now what our equation says is it says to take that value. So that's going to be x plus h plus 3. Then to subtract your function f of x. Now since I have more than one term, I'm going to put it in parentheses. And it's a good idea just to always be in that habit, because as we remove our parentheses, then we're going to have to change our signs. All divided by h. So let's remove our parentheses. We'll have x plus h plus 3 minus x minus 3 divided by h. Now what's going to happen in this step is, and this will always happen, if it doesn't happen then you need to go back and check your work. What's going to happen in this step is every term that doesn't have an h is going to drop out. It's going to subtract out. Well, let's see. We've got x minus x. That's 0. We have a positive 3 minus 3. That's 0. So what we're left with up here is h divided by h, which is 1. So our difference quotient then turned out to be 1. And that's going to correspond then to what the slope of our line is. Okay, let's look at another. And I know the first few times I saw the difference quotient, I thought, ooh, this is going to be really hard. But if you go through it in an organized way, it's not very difficult. Okay, we've got f of x is equal to 2x minus 5. Now that's our f of x. We also we're going to put it into our difference quotient. So that means we need to find out what f of x plus h is. So again, we're going to go through. Wherever there's an x, we're going to put in x plus h. Okay, now we're ready to use our difference quotient. Our difference quotient, remember, is f of x plus h minus f of x all over h. So f of x plus h, well, that's going to be 2 times x plus h minus 5. And I'm just going to write that in this time, and then we'll remove our parentheses. Okay, minus f of x, and I'm going to put it in parentheses because there's 2 terms, 2x minus 5 all over h. Okay, let's remove our parentheses, so we'll distribute 2x plus 2h minus 5 minus 2x plus 5, a negative times a negative, divided by h. Well, 2x minus 2x is 0, minus 5 plus 5 is 0, so I have 2h over h equals 2. Well, that should make sense because we know, again, that was a linear equation, and the slope of that line would be 2. Okay, let's look at one that's not a linear equation. So this one we wouldn't know the answer to. Okay, let's take our function f of x is equal to negative 2x squared plus x plus 5. Now we know that this is a parabola that opens down. So what we're going to come up with is an equation for the slope at any particular point. And and it will change as you go around your parabola. So we've got our equation here. So let's first of all, let's find out what f of x plus h is. And it may be easier just to do this first instead of trying to do it all in our equation as we go through. So what that means is take the function f of x, and so wherever there's an x, we're going to plug in x plus h. So we have negative 2 times x plus h squared plus x plus h plus 5. Now, you can go through and put all of this on top of your, into your formula. And I usually do, I'll go ahead and do that at the beginning, and then I go through and I simplify. It gets kind of long and involved, but it's okay. So I'm going to write all of this. I want my f of x plus h, negative 2 times x plus h squared plus x plus h. I put a 5 there. That should be an h. I'm sorry. X plus h plus 5. Okay, that's my f of x plus h. Now, I'm going to subtract my f of x. Again, I want it in parentheses because it has more than one term. So negative 2x squared plus x plus 5. Having trouble putting my 5's and my h's. I want to plus 5 all over, h. Now, we've got to go through and do our arithmetic. We're going to have to square a binomial. And so I'm going to go ahead and square it. You can go off to the side and put x plus h times x plus h, or if you know the pattern for squaring it, then you can just go ahead and use it. After a couple of times, you're going to know what x plus h squared is. So it's x squared plus 2xh plus h squared. And let's remove these parentheses, x plus h plus 5. Then it's going to be a plus 2x squared minus x minus 5 all over h. Well, I still need to remove these parentheses. So I'll have negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5 plus 2x squared minus x minus 5 all over h. And we could have gone up here when we were doing f of x plus h and go ahead and do the multiplication there and all of the simplification and just write it in. Now, we're ready to combine. And if you remember, what I said earlier was every term that doesn't have an h in it should drop out. Well, we have a negative 2x squared and a positive 2x squared. We have a positive x and a negative x. We have a positive 5 and a negative 5. And so what I'm left with is negative 4xh minus 2h squared plus h all over h. Now, we want to simplify this, and we do that by factoring. Remember, you never cancel until you factor. Well, all of these have a common factor of h. So that's h times negative 4x minus 2h plus 1 all over h. My h's are going to cancel, so I end up with negative 4x minus 2h plus 1. And that will give me, that is an equation that will give me the slope for my graph at any point. And as you get on into calculus, you'll learn what to do with that 2h. Okay, let's look at another one, because again, this is a very important formula and one that you're going to need to be able to work through. But it's, again, it's something that's very mechanical. Let's say we have f of x equals the square root of x minus 1. So we've got a radical. Well, let's first of all figure out what f of x plus h is. That's going to be the square root. Wherever there's an x, I'm going to put in x plus h minus 1. Okay, so we're going to have f of x plus h, so the square root of x plus h minus 1 minus the square root of x minus 1 all over h. Okay, now we're going to do something that you may not ever have done before. We talk about never leaving a square root in the denominator. And so we're used to doing something called rationalizing our denominator, where we multiply it by the conjugate. Well, in this case, what we're going to do is we're going to rationalize our numerator. And we're doing this because we're wanting to get rid of that h in the denominator. And so what we're going to do is we're going to rationalize our numerator. We're going to multiply both the numerator and the denominator by the conjugate. So that's going to be x plus h minus 1 plus the square root of x minus 1. This is going to be the square root of x plus h minus 1 plus the square root of x minus 1. So all we've done is multiply this by 1. We haven't changed any values. Now, we know that when we multiply conjugates, we can use that pattern of a plus b times a minus b is a squared minus b squared. We don't have to deal with those middle terms because they drop out. We have a minus ab and a plus ab, and they always drop out. Well, when you multiply conjugates, this is a pattern that you're following, the difference of squares. So all we're going to have to do is multiply, or take our a square, which when we square the square root of x plus h minus 1, we're going to get x plus h minus 1. We're going to square our last term, which will give us x minus 1. Now, it's a minus, and then that last term squared, which we'll need to put parentheses because there's two terms, x minus 1. Now, for the denominator, I'm not going to distribute. I'm going to leave this written as h times the square root of x plus h minus 1 plus the square root of x minus 1. Make that a little bit clearer. Okay, now when I remove my parentheses, I'm going to have x plus h minus 1 minus x plus 1 plus 1. Over h times the square root of x plus h minus 1 plus the square root of x minus 1. Well, notice in the numerator, my x's cancel, my 1's cancel, and I end up with h over h times the square root of x plus h minus 1 plus the square root of x minus 1. My h's will cancel, and so my final answer then is 1 over the square root of x plus h minus 1 plus the square root of x minus 1. Now, our steps weren't super difficult. As we went through, it kind of looked like it might be complicated, but because we had these conjugates, then we could follow our pattern, and we ended up just squaring the binomial, which got rid of our radical, squaring this binomial, which got rid of our radical. And we're not worried about having radicals in the denominator here. You might say, well, I ended up with a radical in the denominator. That doesn't matter. Right now, we're going to stop at that stage, and we're going to leave it with the radicals in the denominator, so we didn't have to rationalize that. So this is the idea then of using the difference quotient, and it's something that we deal with, and you will see it again. It's going to be the foundation for finding derivatives once you move on into your calculus. Right. The next thing we want to look at is what we call piecewise functions. And a piecewise function is where you're talking about using one function for a specific range and then using a different function for a different part of your domain, not your range, but your domain. And so sometimes your graph look like this. You might have a linear function up to this x, and then maybe from that x you have a different linear function. And there are a lot of different areas where you use this. One of the ones that I always think of is a lot of times your water bills. If you live out in a place where you have to figure your own water bill, well, you pay a certain rate up to so many gallons, and then you pay a different rate as you move on from that, and then maybe even up to another one, you pay an even different rate. So as you're going through, it's a graduated thing, and what you pay changes. And so this would be an example of a piecewise function. Now, we're going to look at a few of these and just evaluate some piecewise functions. We won't spend a lot of time looking at different problems that deal with piecewise functions, but just mainly going through and evaluating it. So the first one we want to look at is f of x is equal to. Now, what we're going to do is we're going to write it as a set. So it equals 3x plus 5 if x is less than 0. It's going to equal 4x plus 7 if x is greater than or equal to 0. Let's look at this and how it would look on a graph. If we looked on a graph of this, and we've got one drawn here, we can see that as x is less than 0, then we have our function, and we can check that we had a slope. We went up 3 to the right 1, up 3 to the right 1, up 3 to the right 1, all the way up, and that our y-intercept was 5. Now I put an open circle here because it didn't say that it equaled 0. So x could not be 0 on this function, and it would keep going. Then our other function was 4x plus 7. So that meant that our y-intercept was 7, and we went up at a rate of up 4 to the right 1. And I've got that one off just a little bit. It should just be to the right 1 here. So let me go back and correct that. So we're going to have our intercept at 7, and then we're going to go up 4 to the right 1, and it would look about like that. So we've got our graph, and you can see then that for one value, if you're picking x's that are less than 0, you're going to use this equation. If you're picking values to the right of 0, then you have to use this other equation. So this is what a piecewise function would look like if we graphed it. Now, what we want to do is go back and evaluate it. So let's say that we have this, and we want to find our f of, let's say we want to find f of negative 2. Well, what we do is we decide which one of these we're going to use. Well, negative 2 is what's less than 0, so we would plug it into this function. And so 3 of negative 2 plus 5 would be negative 6 plus 5, or negative 1. And if we went back and looked at our graph, we can see that when x is negative 2, then our graph was at negative 1. Our equation was. Now, if we wanted to look at f of 0, okay, for f of 0, both of them ended here at 0, or one ended and the other began, but this is the one that equals 0. So this is the equation we would have to use. So we would substitute in 0 for x plus 7, and that would give us 7. And we know on our y-intercept was 7. If we want f of 3, well, 3 is greater than or equal to 0, so again we would use this function. And that would give us 12 plus 7, or 19. So this is an example of how you would evaluate a piecewise function. Let's look at another one, and we're not going to graph this one, but this one is h of x is equal to, it's the set, it's x squared minus 25 over x minus 5. That's if x doesn't equal 5. It is 10 if x equals 5. Now, the reason up here it's talking about x can't equal 5. If x equals 5, we have 0 for the denominator. So we're using this function for all of our values except x equals 5, because at that point it's undefined and we don't get an answer. And so what we've done is we've supplied what an answer will be if it is 5. And we've kind of filled in that hole on our graph. So if we want h of 7, well, 7 isn't 5. So we would use our function and we would have 7 squared minus 25 over 7 minus 5, which would be 49 minus 25 over 2, which is 24 over 2, or 12. Okay, if we want h of 0, well, again, 0 is not 5. So we would have 0 squared minus 25 over 0 minus 5, which is negative 25 over negative 5, or 5. If we wanted h of 5, well, that is a 5, and so at that point it just equals 10, and there's not any computation to do. So this is how you go about evaluating a piecewise function. You simply substitute in, but you have to look at what your domain is over here to know which function you substitute into. What we want to look at now is what we call increasing or decreasing functions. And we want to look at some of our definitions for what we mean by increasing or decreasing. So right here we have got that if x sub 1, and in this case we're going to put a less than, if x sub 1 is less than x sub 2 and y sub 1 is less than y sub 2, then the function is increasing. Now remember, another way we can put y sub 1 would actually be f of x sub 1. It's the y value that goes with x sub 1. And y sub 2 would be f of x sub 2. And sometimes you'll see it written this way. But what we're talking about here is if we have a graph, and here we have x sub 1, and here we have x sub 2. x sub 1 is less than x sub 2. And on our graph, whatever's going on here, the y value that goes with x sub 1 is less than the y value that goes with x sub 2. Our y value here and our y value here. So when this x sub 1 is less than x sub 2, the corresponding y values are also in that same order, then it means our function is increasing. Our function is getting larger. Okay, if x sub 1 is less than x sub 2, and y sub 1 is greater than y sub 2. Okay, what we're saying here is this is our x sub 1 and our x sub 2, but our y values are getting smaller. As we're going in, as our x's are increasing, our y values are decreasing. This is the y sub 1 that goes with it, and down here's our y sub 2. So y sub 1 was greater than x sub 2, then our function is said to be decreasing. Then we also have what's called a constant function. And in a constant function, if x sub 1 is less than x sub 2 and y sub 1's equal, your y's are the same, then your function is said to be constant. So on a graph, if we're looking at this, here's our x sub 1, our x sub 2, but our y values are the same. This f of x sub 1 is the same as this f of x sub 2. Our f of x sub 1 equals our f of x sub 2. And I tried to write it both ways with your function notation and then just with your y's because you're going to see it both ways. And so this is what we call a constant function. Now what you're going to need to be able to do is to take a function and tell the intervals where it's increasing and where it's decreasing. So if we had this as our function, and we're doing something like this, so our function's going on forever, and let's say this is negative 2, that's our negative 1, and 0, and probably this isn't quite the same as to scale, but let's go ahead and do this, and let's do this as 3. And so this is at 1 and at 2. Now, if we look at our graph, from here all the way to this point, we're increasing. Well, that point is at negative 1. That's the point where we change directions. On this side of negative 1, we're increasing. On this side of negative 1, we're decreasing. So if we look at our graph, then from negative infinity to negative 1, our function is increasing. Okay, so now at our value of negative 1, our graph is starting to go down, and it goes down to positive 1. At positive 1, we change directions and we start increasing again. So for the interval from negative 1 to positive 1, our function is decreasing. So from negative 1 to positive 1, we're decreasing. And then from positive 1 all the way to infinity, it looks like we're increasing. And so from 1 to infinity, we're increasing. Now these places where we change directions are called relative maxima or relative minima. And the reason we don't say it absolute, because this is it's a high point, but we can see that our graph keeps growing, so it's not the highest point on the graph, but it is a place where we change directions. So in this case, we have what we would call a relative maximum at -1. So uh, at x equals -1, we have a relative maximum, and okay, and so that would be the location of your relative maximum. Now we recognize that the relative max is a point. We're telling where it's located. So this isn't the equation for a line. We're just saying it's located at -1. If we wanted to know what that relative maximum was, we would have to look at what the y value was with this one. And so let's just make that +1. So the relative max is +1. So it is +1 is your relative maximum. Now we have a relative minimum at x equals +1, and let's make that relative minimum -2. The relative minimum is -2. So we can have what we can deal with our increasing and decreasing functions. We can also deal with relative maximums and minimums. Let's look at another graph. Let's say we have as our graph something that looks like this. Okay, so that's -2 there. So in this case, our graph is increasing from -infinity to -2. It's increasing. From -2 on, then it is constant. So from -2 to +infinity, it's constant. Okay, let's look at one more. Need a new page. Let's say that this is our graph. So this one has lots of changes. And we're going to make this point, let's make that 1, 2, 3, 4, and okay, let's look and see where we're increasing. Now, just to make it a little bit easier, you can see that we're increasing to here, and then we stop. We're not increasing anymore after that. So if we deal with our increasing, then from -infinity to what, -3, we're increasing. Now that's not the only place we're increasing. So if we wanted to go ahead and put the other place that we're increasing from here to here. Our function is also increasing. So let's go ahead and put all the places where we're increasing, and that would be from 0 to 1, 2, 3, 4. Our graph is increasing. Now we want to know, well, where's our graph decreasing? Well, from this point down to here, we're decreasing, and we're decreasing all the way from there. So we're decreasing from -3. I didn't put over here, this was increasing. We're decreasing from -3 to 0. And from what? 4 to positive infinity. We're decreasing. Now we have some relative maximums and minimums. When we change from increasing to decreasing or decreasing to increasing, then we have what's called a relative maximum or minimum. So at this point, we have a relative maximum. And so we have a relative maximum at x equals -3. We also have a relative maximum here where we changed from increasing to decreasing. And so we also have a relative maximum at x equals 4. Now, at -3, our relative maximum is 3. At 4, it's also 3. Now here we change from decreasing to increasing, so we have a relative minimum. Our relative minimum is at x equals 0, and our relative minimum is -3. So you should be able to tell where a function is increasing, where it's decreasing, and then also to find relative maximums and minimums. Now we have a little bit more to look at, and we're going to look at this on the next lesson.